Today we're going to look into transient response. This will be the last lecture before the midterm after the reading week. The content will be included in the midterm. So from lectures 1 to 13. We're going to continue today the analysis of second order response and look more specifically how we can characterize the performance of a second order system and the characteristics of a time response, such as, for example, how much time it takes to reach a steady state. If there is any overshoot, can we quantify that and what affects these parameters? So the objective for today is to understand the concept of these metrics that characterize a second order response and simply model them so that we can develop a controller that will meet certain design requirements in terms of settling time, in terms of how long it takes to settle, and in terms of overshoot, that is how much we can let the system go beyond the final state before it reaches the final state itself. So there are many applications of this concept. Here is one. We have an insulin pump that injects a certain amount of drug to control the blood sugar level. How can we design this system, a controller for this system, such that we want the system to reach a steady state within a certain amount of time, but never exceed a maximum threshold. We never want the output to be beyond a certain value. How can we now tune this system to meet these requirements? Here's another critical example. It's an anesthetic machine that sedates the patient without human intervention. We are again controlling the amount of drug in the system by simply by developing a controller for the machine. And you don't want any overshoot to happen, which means that the system, if you want a amount of drug of, let's say, 1% in the or 0.1% in the blood, we can't afford that percentage to go beyond that value before it settles at 0.1%. So we want a system that has no overshoot. How can we develop a controller to make sure that this never happens? So again, we go back to the concept of transient and the steady state response. So two phases in the system. The first one is the transient. As we saw, we can have systems that we will assume a sinusoidal component, an exponential, or both, and before they reach a final value as a steady state value. Here we have the time response for a step input. And depending on how we tune the system, we can go from a overdamped system to a underdamped system, and even make the system unstable depending on how we tune it. All right, so it's important to characterize now this system, put numbers on how the system behaves. How long does it take to reach a steady state? Basically, what is this time here it takes to reach a steady state? What is the maximum value it can reach? That is, what is the overshoot beyond the steady state value? How can you characterize these? And how can we tune the system to meet certain requirements, such as we want the system to settle within 2 seconds, and we don't want the system to go beyond 5% of its final value. So to do that, now we are talking about controlling a system. And when you're talking about controlling a system, we need to also think about a control structure. So before we go into this analysis, let's take a look at a very simple control structure here. This is a closed loop system, and we addressed this in the past lectures. So here we have a system that has a transfer function 1 over tau s, and that is the system we want to control. That is the plant we want to control. Now notice that now there is a feedback loop from the input to the output, and there is a gain k. So let's see what are the functions of all these elements in the system here before we go on. So again, the system to be controlled is here. This is the plant or the system itself. This is the controller that we decide here to just have a proportional gain k. Here we have the input, and here we have the output of our system. The input to the transfer function is here to the process, and the output is there. Now, what have we done here? Notice that we are doing a closed loop control, meaning that our output is constantly monitored and we compare that with the input, we multiply that by a certain value, and that's what we apply to the plant. So this characterizes our first closed loop system. And there are several elements that we can identify here. The first one is, of course, the input. This is the desired value for the output. So if the controller works well, and we put let's say a step input here of 1, the output will go to 1, right? Ideally. Because what are we doing again? We are comparing through this summation here, the input and the output. And the difference here is multiplied by a gain, and that is what we apply to the plant. The output here in this summation is the error. The error is simply how far away we are from the desired output. That characterizes the error in the system. We now multiply this error by a constant k, and that's the control action we give to the plant. Let's say, for example, if you want to control the amount of, let me think about one clear example. If you want to control the amount of a drug in the system, in the body, and we have here a plant that is a machine that injects that amount of drug, the input to the machine could be how much we open a valve, for example. And this amount now becomes proportional to the error between the input and the output. If we are exactly where we want, that is, there's no error, the desired input and the desired output are exactly the same, there is no error, this is 0, we don't open the valve. So long as there is a small difference between the desired and the actual value, we multiply that by a constant that we need to design, and that will give then the amount of opening we apply to the valve. Okay, and this system now continues to operate like that. So to analyze this system, we need what I'm going to call the closed loop transfer function. This is the transfer function of the system. This is the transfer function of the controller. But we need the transfer function of the entire system, R y over R. How can we calculate that? So let's assume, for example, let's just call whatever we have here, the entire function here. Let's call this function h of s. If this entire function here is h of s, can we establish a relation between y, r, and h? We can say that y of s is equal to what? What would be the expression for y of s? Isn't y of s this value here multiplied by h of s? Wouldn't be the error times h of s. So y of s would be r of s minus y of s multiplied by h of s. Does this make sense? Can you see that relation? Tell me if it's not clear, because this is very important. Is it fine? Is this clear? If not, yeah,
makes sense.
Okay. If anybody doesn't understand this, let me know, because this is very important. So let me summarize once again. So this is h of s. If you take this value here, whatever we have there, and multiply by h of s, you get y. So we can is this signal, the error, which is r minus y times the function h of s. Okay. So if I don't hear anything, I'll continue here. Now what can you do? We can multiply this out and move all y's to the other side. So y of s plus y of s h of s equals to r of s times h of s. Can factor out y here. 1 plus h equals to r of s, h of s. And now we can find our transfer function output divided by the input equals to h of s divided by 1 plus h of s. This is the closed loop transfer function in this system. It will always follow this format, provided that we have a unit feedback loop here. There's no function in there, but you can expand this equation to include a function. For now, we don't have it. When you have a system, when you close the loop like that, we always end up with a transfer function following this format. The line function divided by 1 plus the line function. If this signal here is positive, then this signal here will become negative. Okay? But when it's negative, it's positive like that. Okay. So what is the closed loop transfer function for our system now? Well, we have y over r equals to, what is h of s? Well, h of s is k divided by tau s, right? This function multiplied by that function. And this is divided by 1 plus itself, k over tau s. What can we do here? We can find a common denominator. The common denominator here is tau s. So we have tau s plus k. This tau s here cancels out. And if we divide both the numerator and the denominator by k, we have 1 over tau over k s plus 1. Okay, so what can we see here? We can see that our transfer function follows a well-known format. It's a first order transfer function. It has a time constant, but it also has this gain k here that we can control now. The time constant is inherent to the system, that we have no control over it. It belongs to the system itself. It depends on how it works, and we cannot change it, but we can change k. K is up to us as designers to choose. And what are we doing by changing k in the system? Well, clearly, when we change k here, we are changing the time constant of the closed loop system. Originally, the system has this time constant tau, but by adding the closed loop controller, you see now that we have control over the time constant. The greater k, the lower the time constant. The greater k, the faster the system reacts. Okay, what is the time response for this? Because it is a first order system, we are dealing with an exponential component in the output. And this exponential component can now be controlled based on the value of k that we can choose. This proportionality constant that in the example I gave would give us the aperture of a valve based on the error in the system. Are there any questions here?
Professor, just can you again the part when which part is negative, the other part become the positive?
Yes, so if this sign here becomes positive, we can redo the whole thing. This sign will become positive. When you move it this side, it becomes negative, so this sign flips. You don't need to take that as a rule. You can redo the whole equation, and you'll notice that when this is positive, then this becomes negative.
Okay, just some math things.
Yeah,
okay,
it's just the math. Any other questions?
Professor, what did you say about k affecting the time constant? You said if you increase k, what happens?
Where is the time constant of our closed loop system? Is whatever multiplies s. Right, so tau is a constant from the system when you divide that by k. This element, this entire thing that multiplies s, is now the new time constant. So the greater k, the smaller the time constant, the faster the system reacts. Makes sense. Why does it make sense? Because if we increase k, we are saying, well, for a very small error, open the valve all the way. If k is small, we are saying it will need a large error to open a little bit the valve and change the system behavior. In the example I gave, right? So it makes perfect sense from the block diagram perspective and from the equation Okay, so what is the limit? Then let's say, let me give you another example. Let's say this function here is a robot arm that is operating on a patient. And the input to this robot arm is a voltage. And we want the input to, of course, follow the output to follow the input. So now we know that at the higher K, the faster the robot reacts. But what is the limit for K? What is the physical limit for K? Theoretically, there is no limit. We could make K tend to infinity, and the system wouldn't even have a transient, would just reach steady state right away because the time constant would be so small. But remember that a K is a gain that we need to establish here. So if this is a voltage, there is a physical limit for K because we don't want a small error here to generate, let's say, 1 million volts here. We can't do that. We need this output to be reasonable within, let's say, 48, 100 volts maximum. So we need to tune K to also respect the limitations of the hardware we are working with, even though in theory there is no limit for it. So that's how we got this transfer function. All right. So the question is, how does K now influence the steady state response or the transient response of this system? To do that, we need to establish some signals to analyze the performance of the system. So the first one is the well-known step response, where the inputs to the system would be 1 over S, and a ramp response can also be used as a testing signal. In this case, the input would be 1 over S squared. You're going to give both of these values to the system and see what happens. So we can go through the entire derivation here, but I think this is trivial. So I'm going to skip it. All I did here was to take the transfer function, the closed loop transfer function, multiply that by the respective input, 1 over S and 1 over S squared, and then do the inverse. And that's what we get if you plot the time response. Now notice something here. This is the step response. And notice that at the higher K, the faster the system reacts, the faster it reaches its final value. If you look at the ramp, the transient is down here. We can also see that at the higher K, the lower, the less time it takes to reach a steady state. Okay. So K doesn't influence the steady state for the step. Sorry, you can see my hand here for the step, but it does influence the transient response. All right. Are there any questions? I see a few messages on the chat, but I can't see it. So if there's anything important there, let me know. I'll try to answer.
Oh no, I was just asking if it was lagging for anyone else. I think it's my Wi-Fi.
Okay. All right. Any questions? No? Okay, so that's what happens to a first order system. The value of this control gain reduces the time constant. The higher K, the faster the response. What is the maximum control gain K? Theoretically, there is no limit. Physically, we need to watch for saturations in the system for the limitations of our hardware. Right? But in theory, there would be no limitation.
Professor, just what's the second graph?
Second graph is the ramp response.
Okay, thank you.
Yeah. First one is the step, the second one is the ramp. So the input to the first one is 1 over S. For the second one is 1 over S squared. Okay. Now let's look at second order systems. If you want to do a second order system, what is going to happen now? Well, in the first order system, things are easy because we know that it can only get an exponential in the output. But if you now do a second order system, this value of K will change everything. It will change the natural frequency of the system, and more critically, it will change the damping ratio. And the damping ratio can now go higher or lower than 1, which will affect even the shape of the time response. If we follow the same procedure that I did to find the transfer function of the previous system, we can find the transfer function for this one. How would we write that? It would be y over r equals to h of s divided by 1 plus h of s. And what is h of s? H of s is this entire line function here, k over s plus a. We can do it quickly here, k s plus a divided by 1 plus k s plus a. Find a common denominator in the denominator of the equation, k s plus a divided by common denominator is s plus a. This gives s plus a plus k. Now these two cancel out because they are the same, and you're left with k over s squared plus as plus k. A very simple math, just follow the standardized equation there. So that's the transfer function in the closed loop form. We can now write this in the standard form. And if you write this in the standard form, what can we see? We see that now our gain k is showing up in the denominator, and that's a problem because now we can change completely the characteristics of the system. We can now see that omega n is square root of k. So the natural frequency depends on that. And if you do 2 zeta omega n equals to this constant k, now 2 zeta omega n equals to a, zeta is a over 2 square root of k. So now both the natural frequency and the damping ratio are functions of k. And now we need to watch out for cases where the system may even go unstable depending on the value of zeta. We can now have underdamped system, overdamped system, and even make the system unstable by changing this value of k. Any questions here? No? Okay, so our observation now is that when you have a second order system with that specific control structure, both the damping ratio and the natural frequency are functions of the control gain that we can choose. And this will strongly affect the time response. Depending on the value of k, we may have a damping ratio greater than 1, in which case the time response is an exponential component. We can have, depending on the value of k, a damping ratio that is smaller than 1, in which case the time response will follow this format. This is the step response to the system. And you see both components here, the exponential component and the sinusoidal component. We see that now they both are affected by zeta and omega n, which are now functions of k. So now, depending on the value of k, once again, we can make the system go from between each of these formats here. The first example would be when k is greater than 1. When k is greater than 1, the poles are located on the real axis, and you have a, excuse me, not k greater than 1, zeta greater than 1. For a given value of k, that will make zeta greater than 1. For example, here, when k equals to 0.25 for a given value of a, zeta will be equal to 1. And that means we have a critically damped system. Both poles are located on the real axis. If you now keep increasing k, remember here from the equation we just saw, inversely proportional to k. So the higher k, the smaller zeta. And now as we increase k, we make the system more aggressive, more responsive. But now k goes below 1, and then we start to see oscillations. And you see that the higher k goes, the smaller zeta, and the more oscillations appear in the system. What is happening to the poles? Well, the poles are moving away from the real axis and moving closer to the imaginary axis. The system tends to be a little bit more unstable. It's still stable though, because the real part of the pole is positive, is negative. Right? But we see now that we can completely shape the output of the system. We have full control over it. If we want the system to react fast, but we allow some overshoot, then you can operate with a system like this. You see that after this much time, actually even lower than that, like around here, it is very close to its final value. So the system reacts very fast, but it overshoots a little bit. If that cannot happen, we can opt for lower value of K. The system will take longer to settle, but it will not overshoot. And as designers, now we need to come up with metrics to define the overshoot and to define how long the system takes to settle. So for a second order system, now we have all this range to work with. We have exponential and an exponentially decaying sinusoidal waveform.
How did you get equation 1?
Equation 1 is from the last lecture, when we have complex conjugate poles, when zeta is between 0 and 1, the time response will be like that. That comes from a table of inverse Laplace transform for complex poles. Right? When the input is 1 over s. Okay, that's from lecture 12. But what I'm basically doing is splitting this into imaginary poles, doing partial fraction, taking the inverse Laplace, and we'll fall into that.
Oh, okay, thank you.
But that will take a while. Okay, so now that you're dealing with second order systems, we have to characterize this time response and create some metrics. So here is a typical second order response for a underdamped system, underdamped, which means that zeta is comprised between 1 and 0. And we have several metrics that we could establish here. And these are the standard ones using in control systems theory. The first one is the overshoot. The second one is the settling time. And you also have something that's like peak time and rise time. The most obvious one is the settling time. So the settling time, we are going to call that a TS, and is the time the system takes to reach 2% of its final value. You see that past this point here, the output enters a zone, a range, it oscillates within that range, and that range is within 2% of the final value. So in this case, the final value is 1. So long as the output stays between 0.89 and 1.02, 2% of the final value plus or minus, the system has reached, we can say the system has reached steady state. The first point where it occurs, that's the settling time. Okay, some textbooks would use 5%, but most commonly we do 2%. The second important one, so that's the settling time. The second characteristic is the overshoot. And the name says it all. Overshoot means how much we go beyond the maximum value of the system. And that will occur at the peak time TP. When the system first starts, it overshoots to this maximum value MPT. That's the peak time. And this difference between the final value and the peak time, the peak value at the peak time is the overshoot, is the percent overshoot, is a percentage of how much more it goes beyond the maximum value. So if this reaches, let's say 1.2, we would overshoot by 20%. 20% more than the final value, which is 1. Okay. And then the rise time would be the first time we cross the final value. But this one we are not going to use. Okay, so let's focus on the percent overshoot and the settling time. So let's do the percent overshoot first. For a unit step input, the percent overshoot is defined as follows. The maximum value or the peak value minus the final value divided by the final value times 100. So in our previous case, if we reached 1.2, would be 1.2 minus 1 divided by 1 times 120%. So if you want to find now an expression for this, we need to find the maximum value of the output. And how do we find the maximum value of a function? Let's look at this big function here. In math, if you remember from calculus, if you want to find the maximum value of this function, what do we do? How do you find the maximum value of any function? Anybody? Take the
Find the
derivative.
derivative. Oh,
Okay,
and set it
exactly.
to 0. Sorry.
Set the derivative to 0. With this, what do we find? We find the time t first, where when this the function, the derivative reaches 0. So it will be, let's call that a pt. And once you replace pt back into the original function, then you find the final value of the function. So take the derivative of it, set it to 0. We solve for the time, and that time gives the time where the maximum occurs. So take that time, input it back into the equation, and voila, we have the maximum value itself. So that's what we're going to do here. I'm going to skip all this derivation because it will take forever, but that's the idea. We take the time response, we differentiate to 0, and we get the peak time. Here is the peak time, the time where the peak occurs. We take the peak time, input it back into the equation, and solve for the peak value, or the maximum value, or the value of y at the peak time. And that's what we get. That's equation 4. And now we are ready to take equation 4, the maximum value, input it back in there. And when we have a unit step input, then final value is 1. And you can calculate the percent overshoot as follows. So note this equation, highlight this equation. This equation is very important. This gives us the percent overshoot in the system. And notice something interesting. It is a direct function of zeta. It's a direct function of the damping ratio, which according to our previous analysis is now a function of k. So by changing k, the overshoot will change. So 100 times exponential of negative zeta pi divided by square root of 1 minus zeta squared. So now this was derived for an overdamped system. Sorry, an underdamped system. It was derived for an underdamped system. So this can only work for zeta between 0 and 1. This does not work outside of this range, right? Because the equation we got to start with was derived for this condition. What is the overshoot in a overdamped system? What is the overshoot when zeta is greater than 1? What is the overshoot when zeta is greater than 1?
There is none.
There is none. It's 0. Very good. This equation then only applies for underdamped systems, meaning that zeta is between 0 and 1. Okay, so that's the first part of the story. Here is the percent overshoot. So highlight this equation. We're going to use this all the time. Now, the second measure of performance is the settling time. And the settling time, we said, well, the settling time is when the system reaches 2% of its final value. Look at the step input here, the step response. And we see that we have the final value right there. And we see this exponential times a sinusoidal that will eventually decay to 0. So if you want the system to be within 2% of its final value, then the exponential here that is bringing the sinusoidal to 0 must be less than 0.02. If that is the case, then the final value is within, then the system is within 2% of its final value. In fact, all we need is to take the exponential here and make the exponential equal to 0.02 and then solve for it. Yeah, and you see that this will occur at a time Ts, that's the settling time. We take the natural log of both sides of the equation, we can solve for the settling time, and we get an expression like that. We take it one step further, and we can see that the settling time is given by 4 divided by omega n times zeta. 4 divided by omega n times zeta. Again, characteristics of the functions of the control gain. Okay. And here we can use this to define the time constant of a system in a second order system. And the time constant in a second order system is always defined as 1 over zeta times omega n. So we can say that the settling time is 4 times the time constant. The settling time is equal to 4 times the time constant of a second order system. Okay. Any questions? So this is the second equation to note. To highlight, this is a very important equation that gives us how much time the system takes to reach 2% of its final value, and is only a function of its damping ratio and natural frequency. Any questions? No? Okay. So now something else to note here, we see that in the denominator we have zeta times omega n. The zeta times omega n. And when you look at our second order transfer function, the denominator here, and we find the poles of the transfer function, we see that they show up here and there. Zeta omega n is in fact the real part of the pole. Now these are the roots of this polynomial. This polynomial is the denominator of the transfer function. So these are the poles of our transfer function. And the real part of the pole is precisely what affects the damping ratio. Sorry, it's precisely what affects the settling time. That is a function of the damping ratio and the natural frequency. So what can we state? We can say that the settling time is inversely proportional to the real part of the poles. Another way to say this is the farther the poles are from the imaginary axis, the faster the system responds. The farther the poles are from the imaginary axis, the faster the system responds. The farther they are from the imaginary axis, the bigger their real part is. And then they move to the left. But the more to the left they are, zeta omega n increases, which means that the settling time decreases based on equation 8. So those poles that have real parts very close to the imaginary axis will take longer to reach the steady state. And those that are far away will have a very small transient that vanishes very fast. Okay. Very interesting question for a hypothetical midterm. Let me give you an example here. We have this transfer function 5 over s squared plus s plus 5. Here from the second order standard form, we can say that omega n is square root of 5 and 2 zeta omega n equals to 1. So zeta is 1 over 2 square root of 5. Using this, we can calculate the time constant, and the time constant turns out to be 4 seconds. We saw that the settling time is supposed to be 4 times the time constant, which means that within 8 seconds, the system must reach 2% of its final value. Here is the time response to a step input of that function plotted in MATLAB. And you can see that that actually is true. Here is 1 time constant. Here we have 2 time constants, and you see that you're getting closer to the final value. Here we have 3 time constants. And here you have 4 time constants. And you see that precisely when we reach the 4 time constant, and oscillations are very small around the final value of 1, and the system has reached indeed the steady state. The settling time is right there. Okay, overshoot is here. You could calculate that as well based on zeta. Okay. Any questions?
Professor, is that possible? You draw the x-axis to show that when the farther pole from the imaginary axis, the faster the system is?
Yeah, we can reiterate that if needed.
Oh, okay.
Yeah, next slide. Okay. Any questions? More questions here? So two metrics to keep in mind: settling time and percent overshoot. So now let's summarize what we discussed in the last lecture and in this lecture. Here we have the poles of a second order transfer function. This would be S2. Each of these poles have a real and an imaginary component. They have a real part here, and they have an imaginary component there. When zeta is greater than 1, the imaginary part will disappear because that becomes a real number. And the system will have poles, two poles located on the real axis. This will give rise to an exponential time response. If we keep decreasing k, these poles will come together, and at one point they will meet. So the two poles are together, and this occurs when zeta is precisely 1. We have two poles that are identical. They are simply minus zeta omega n. Now the other part you see becomes 0 when zeta equals to 1. And at this point here, the system is said to be critically damped. If we keep decreasing, so this is the case for zeta equals to 1. If you keep decreasing zeta, now you'll see that now zeta will less than 1 will make the imaginary part here show up, and these poles will now break away from the real axis, which means that now they have both a real part, negative zeta omega n, and an imaginary part, j omega n square root of 1 minus zeta squared, and negative j omega n square root of 1 minus j squared. One is positive, one is the complement of that, is the complex conjugate of that. And the system now, when zeta is less than 1, is said to be underdamped. Underdamped. If we keep decreasing k, these poles will now start to move towards the imaginary axis. And if they move towards the imaginary axis, the damping ratio is decreasing. What is happening with the real part? The real part is moving towards the left. So this is the right side, moving towards the right, which means that now the settling time, which is 4 over zeta omega n, zeta omega n is getting smaller, the settling time is increasing. The system will oscillate more, and it'll take longer to reach a steady state. And when we reach the imaginary axis, then zeta equals to 0. And at this point, the imaginary part now disappears, and you're left with real part. The real part disappears, we are left with imaginary components only, and the system oscillates. Past that point, zeta is smaller than 0, and the system oscillates indefinitely. We enter the unstable zone. So here we have the summary of what we discussed. 5 cases here of interest. Let's say 6. Greater than 1, we have poles that are distinct to real numbers. The system is overdamped. Equals to 1, real poles but are equal. the system is critically damped, zeta between 0 and 1, complex conjugate poles, underdamped, zeta equals to 0, purely imaginary, we have a undamped system, and greater zeta less than 0, the system becomes unstable. Okay, and you notice now that in the control scheme we have with a unit feedback loop and a control gain, we change completely zeta and omega n now. So we can make a system that was stable, unstable by controlling it with it too aggressively, or we can do the opposite. We can take a system that is naturally unstable and make it stable. As such a bike, for example. A bike is unstable without control, and we keep actively controlling it when we ride the bike to keep it balanced. So it's an unstable system that with a controller becomes stable. Any questions? No? Let's do some, yeah.
Can we see that in the case the zeta bigger than 1, the system is the most stable?
So long as zeta is less than 1, it is greater than 0, the system is stable. A overdamped system is more stable than a system that is underdamped. Yeah, we could mathematically we can say they are equally stable.
Okay, but just like it depends on the time, because if it brings close to the imaginary line, actually the system will respond more faster.
Right.
Faster.
Yeah.
Okay.
Yeah. Any other questions before we do some exercise? Let's try to do 2. And we have time. Let's do exercise number 2, which is easier here. Okay. So to consider this system, calculate the steady state error for a ramp input and select K that will result in 0 overshoot to a step input. What is the first thing we need to do here? What is the first thing we need to do? If you want to calculate, let's say the value of K that results in no overshoot, what is the first thing we need?
Transfer function?
The transfer function. So let's do this. Try to calculate the transfer function. I'll give you a few minutes. Try to calculate the closed loop transfer function. That will be in the form of 1 h of s divided by 1 plus h of s. That's y over s over r. And when you're done, so go ahead, try to do that as I erase here. And when you're done, send me your answer through a private message on the chat. And if you get it right, I'll give you some extra bonus. Okay, so find the closed loop transfer function. Send your answer to me with a private message in the chat. You can send it only to me. And if you get it right, I will add those bonus marks that we got in the last quiz. And in the meantime, I'm going to raise the light board. And I'm assuming that I have you're using your Carlton account on Zoom, so your name should be the same as the one you have on Brightspace, right? Okay, 2 more minutes. Please don't send your answer to everybody, just send it to me. And if this works, then we'll do more bonus quizzes like that. So try to do it properly. So I have about 12, 10 answers. Okay, so all right, 2 more minutes. This time I'm serious. And then after that, answers that come after 10:59 will not be considered. So go ahead. Let's make 11. Okay, until 11. Let's have 2 minutes left.
Professor, during this time, may I ask a question?
Sure, go ahead.
Just want to clarify that what we are talking about, when it's close to more zeta, more close to the imaginary axis, the system going to be faster. Then the setting time will be I mean, the setting time is longer or shorter?
The settling time is taking longer, but the system will first cross the final value faster, and then it will take some time to settle.
Oh,
right. So the closer you get to the imaginary, there's a combination of zeta and omega n. So it's a bit more.
okay, I think I got it.
Okay.
Thank you. So that means the first time it reached to the expected value, it will be faster, but actually it will taking longer to let the oscillation settling down, settle down, right?
Correct.
Okay, thank you.
Okay. So 1 more minute. Okay, time is up. Now I'm gonna solve it. Let's do it together. So who got the answer? What is your answer? Anybody has a tell me what they got? So if this whole thing here is h of s, so what time is it? So it's 11. So after this time,
K over s squared plus 5s plus k.
correct. So h of s is this times that. So k over s plus 5 divided by 1 plus k s plus 5. What do we do next here? We can find a common denominator. The common denominator is s plus 5 multiplies 1 plus k, and the numerator is I didn't do a good job here with real estate. That. All right, so these cancels that, and we are left with k over s squared plus 5s plus k, and this is y over r. Are there any questions with this derivation? Are we all good with it? Yeah? No? Yep. Okay.
Yeah, makes sense.
Sounds good. So now the question, let's do question B first. Question B says select k that will result in 0 overshoot to a step input. Select k that result in 0 overshoot to a step input. So how would you do that? We could say that a percent overshoot, which is 100 exponential of a negative pi over a square root of 1 minus z squared, Is that, or is it the other way around? Is z squared minus 1 or 1 minus z squared? It's z squared minus 1. Yeah, it's the other way. Nope. 1 sec. 1 minus z squared. Okay, that's right. And I forgot the zeta on top here. We could say that we want this to be 0, but this doesn't work. Why not? We can do this because this expression was derived for zeta between 0 and 1. If you want the system to have no overshoot, then we are outside of this range, and this equation doesn't work. If I wanted the system to have an overshoot of 20%, then this would be 20 equals to that. We just solve for zeta and then try to find the value of k that meets that zeta. But now we want no overshoot, so this equation doesn't hold because it's only valid for this range. And if you want no overshoot, then zeta must be greater than 1. We are not in the range anymore. And the reason I'm insisting with this is that that's a very common mistake the students make. They just equate this to 0 and try to solve for zeta, but that doesn't make sense. This equation is only valid for this range. So if we cannot use this, what can we do? I kind of already gave the answer. We want zeta to be at least 1 or higher. That will guarantee that we have no overshoot. Remember that in the standard form, in the denominator, we can write that as s squared plus 2 zeta omega n s plus omega n squared. So we know that omega n squared equals to 5. Sorry, equals to k. And we know that 2 zeta omega n equals to 5. From this expression here, we have omega n equals to square root of 5. And you can replace it down here. So you have 2 zeta omega n, which is square root of 5. Equals to 5. What is zeta? Well, we want the system to have no overshoot, so zeta is 1. Sorry, I wrote square root of 5 again here. This is square root of k. That's why it's getting confused. So square root omega n squared is k, omega n squared is k, omega n squared is the square root of k. Then replace it here. This is square root of k. Right? That makes more sense. We now have a square root of k equals to 5 over 2. K equals to 5 over 2 squared, which is 6.25. So k equals to 6.25 will give a damping ratio of 1. The system is critically damped. So if you want our system to have no overshoot, should k be greater or smaller than 6.25? At this point, the system is critically damped. So if you want a over-damped system that is no overshoot, should it go higher or smaller than?
Higher.
If we go higher,
I think it's smaller.
let's see. Let's look at the equation here. If we write the expression for zeta, we have 5 over 2 square root of k. So the greater k, the smaller the damping ratio. Right? So we need to go smaller, like lower than 6.25. And if that is the case, then the system has a damping ratio of at least 1 or higher, and there is indeed no overshoot. Are there any questions?
Professor, so in this case, we just assume that zeta were close to 1 because the range of the zeta here is actually 0 and 1. But in this case, we just assume it is 1, and then we get the value of k and know that if we want it to be what we expect, then the k is smaller than this value.
Right, yes. We know that the higher k, the lower the
Okay.
damping ratio, right? So that will give us the maximum value of k before the system becomes underdamped and an oscillation rule starts to show.
Okay, good to know. Just like do some limit things.
Yeah. Yeah. Okay, now let's do part 2 of this question. In part 2 of this question, we want to calculate the steady state error to a unit ramp input, I believe. Or to a ramp input. Let's say it's just a ramp input. What is the steady state error? How do we do that? Well, we have the transfer function. Knowing the transfer function, we can calculate the final value. We'll be able to calculate the steady state output of the system easily. But now what we want to calculate is not the final value of the transfer function. Is in fact the error, and the error is right here. How would we calculate the final value of this function if we had to calculate it? Just the final value of y as time tends to infinity. We would use the final value theorem. And how would we do that? We would take the limit of y times s when s tends to 0. That would give us the final value for this transfer function for a given input r of s. If you want to calculate the final error, you just need an expression for this, and you can do the same. We can take the limit when s tends to 0 of s times the error function. S times the error function. And our input, the problem says it's a, what is the input here? Is a ramp for a ramp input. So if it's a ramp input, then you can say that r of s equals to a over s squared, where a is just the slope of the ramp. So r of t would be at. It's just a constant. Now, if this was a unit ramp, this would just be 1, but to keep it generic, you can just multiply this by a constant. So the Laplace of that is a over s squared. So we have everything now. We have the desired output. We can calculate the actual output by multiplying this side of the transfer function by r of s, which is this. And then now we can subtract them, find the error, and calculate the steady state error. So this can be written as the limit when s tends to 0 of s times, what is the error? The error is here, which is r minus y, r of s minus y of s. What is y of s? Y of s you can take from here. Y of s equals to this entire transfer function. Let me call this g of s times r s, which is a over s squared. Now just multiplying this part, multiplying r of s on this side, moving that to that side, we have the transfer function times the input, that's the output. The classic transfer function. We have everything here. We can now continue the development. The limit when s tends to 0 of s, remember that this s comes from the theorem. R of s is, as we defined here, a over s squared minus y of s, this times r, so k over s squared plus 5s plus k times a over s squared. Are there any questions? Does this make sense?
Yep.
Yeah. Right. Input transfer function times the input is the output. The difference is the error. We can factor out now a over s squared. A over, sorry, let me just do, what is the easiest way to do this? Okay, yeah, so let me do this a bit different. Just make the math a bit easier. We can see that this s here will cancel 1 power of the s squared, and now as can be brought to the front here. 1 minus k s squared plus 5s plus k. We can't take the limit now because we have s here. This would make everything go to infinity, so we need to work what is inside of the equation first. This gives the limit of a over s. And now let's find a common denominator here, which is s squared plus 5s plus k. That multiplies 1 plus k minus k. This is that k there. All right, so this part is what multiplies 1, and this k is that k. So k and k cancel. We have limit when s tends to 0 of a over s times. You see now that the k cancels out here, we can factor out 1s. So s plus 5 divided by s squared plus 5s plus k. Now this s and that s will go away. And now we can do the limit. What is the limit here? What is the limit? When s tends to 0, this s goes to 0, this 2 go to 0, we are left with a times 5 divided by k. Another interesting observation can be made here about k. Notice that the greater k, the smaller the steady state error. What does that mean? The greater k, the closer the output will be to the input. This would be for a ramp input. We have the input like that. That's the desired, which is the desired output. So this is time. This would be r of t. And the output will be something like that. This difference at any point in time is here in steady state. This is this difference. And this difference decreases as k increases. Okay, and the transient is down here. Any questions?
Sorry, just again, what's the graph mean? So it's the input and output?
Yeah.
Okay.
Is this the desired? This is r of t. This is y of t. Right, desired is the input now in our system becomes the desired output. Right, so we ideally the yellow curve here would be exactly as the input, but there is two different things here. The first one is a transient because of the exponential component in the time response, and the second one is this difference here, which is an error, and it's the steady state error. Is the difference between.
So both of them is like like a curve, or one of them is linear?
This is linear because this is r of t equals to a times t. And so the slope here is the arctangent of a. It just depends on that, but it's a line, right? A times t. So if this is t, r of t is just a constant times time.
Yeah.
So
yeah.
depending on a, the slope changes. The other one here is
Exponential?
an exponential plus a constant after it reaches a
Okay.
steady state.
Okay, good to know. Thank you.
Any questions? Other questions?
I'm sorry, did you say that as you increase K, that gap will get smaller?
Yeah, look at this.
Yes.
Right, look, this is the error, so the greater K, the smaller the gap.
So we want to increase K to get a smaller error,
right?
But also decrease it to
avoid
more
oscillations.
damp system.
Yeah. Yeah, and what do we do now? Well, there's no single answer to that. If we increase K too much, we'll see too much oscillations.
So is there a like critical number?
Nope, we need to design the system, and there is no single answer to that question now.
Okay.
It really depends on, let's say, for example, if we want the maximum over 5%, we'll select K at that limit so that the oscillations don't go beyond 5%. But then there's nothing you can do about the steady state error. You have two requirements and they kind of contradict each other. At one point, you have to make a compromise. Okay, so let's do exercise 3. I'm going to erase this. Exercise 3 is very similar. We have the insulin pump from the beginning of the lecture. And we want to control the insulin pump to keep the blood sugar level at a given value for a step input. So we want, let's say, 1% blood sugar level. And we don't want the output to go beyond 7%. So how can we calculate this value of K that makes the system react fast enough while not exceeding 7% of the final value? I'm actually going to change it to 8% because at 7%, the result is a bit funny and it just adds some unnecessary confusion. So let's do 8% instead. So first things first, calculate the closed loop transfer function. So again, 1 plus h of s divided by 1 plus h of s. And in this case, h of s is k times s plus 2 divided by s plus 1. Okay, I have 5 minutes and I don't want to go over time for every lecture. So maybe I should just talk less. I'm just going to give you the transfer function here for the closed loop system. It's just math, and I will post the full solution online. So if we do the closed loop transfer function here, the closed loop transfer function should be y over r equals to k s plus 2 divided by s squared plus s times 1 plus k plus 2k. Now notice the structure here is interesting. Now our plant is the human body. And that's what we're trying to control. The input here to the human body could be the amount of drug we inject that is proportional to the error between the desired sugar level and the actual level. So it creates the error, multiply the error by an arbitrary constant that you need to define. And now this is the amount of drug we inject into the body. The body has its own transfer function that will give now the response based on that specific input. This can be perfectly modeled as a transfer function. I'm not making that one up. Let's assume that we want a percent overshoot of 80%. 8%. No more than 8% instead of 7. What do we do now? Well, from the standard form, we can find omega n and zeta. And you know that the percent overshoot only depends on zeta. And this will be affected by k. So the first things first is that first thing to do is we know that the percent overshoot is only a function of the damping ratio, and that is given by 100 exponential of negative pi zeta divided by square root of 1 minus zeta squared. So from this, we can find the required damping ratio to give an 8% overshoot. You can just replace 8 on this side here, divide that by 100, and then take the natural log on both sides of the equation. And when you take the natural log of this, we get negative pi zeta square root of 1 minus zeta squared. So I divided 8 by 100. I took the natural log on both sides, and that will cancel the exponential. Good here? Any questions here? No? Now there's a square root here. Yeah. Was there a question?
For 8%, is that, do you say 8 over 100?
Well, this 8, because this is already, this 100 here was added here as to make it a percentage.
Oh, okay.
So we just put 8 there. That's actually a very good point. It's a common mistake. So now if you want to get rid of this square root, you can square both sides of this equation. Like that. And then you have the natural log of 8 over 100 all squared, multiply square root of 1 minus zeta squared, and equals to pi squared zeta squared. And from this we get zeta. We can just solve for this equation. Now it's very simple. It's just zeta squared. It will all work out here. And the value of zeta required is 0.73. When is that have 0.73, the percent overshoot is 8%. I will double check this number here because this is a bit too low for an 8%. So it might be something a little different. I don't think this is fully right, but anyways, you get the idea. It's just you get the damping ratio. I'll just double check this calculation before I post the final notes. But here we get the required value of zeta to achieve an 8% overshoot. Now, what do we do with it? What do we do with it? Well, now we can find the value of k here. That will give a damping ratio for this transfer function of exactly 0.7. Now, can you do that? Well, equate this to the standard form. And solve for k, because now k, zeta is a function of k. So we have omega n squared equals to 2k. Omega n is the square root of 2k. We have 2 zeta omega n equals to 1 plus k. Right, that is equals to that. Yeah, the 1 plus k multiplies s. Right, so this is same as that. And we have now 2 zeta 0.73 times omega n square root of 2k equals to 1 plus k. You see here that the only thing left in the equation is k. This will give a second order polynomial. We want to get rid of this square root of 2k, you square this. square that, so we have a second order polynomial to solve for, and we solve the polynomial to find the value of k. In this case is 0.6 by just solving the second order polynomial here. Okay, there will be another value of k that will be outside of the bounds from 0 to 1, and you can discard it. This one is the one that will satisfy the equation. I do have to check this number though, I don't trust it. One thing that you can look right away is that if this number happens to be greater than 1, you did something wrong, because this equation is only valid between 1 and 0, right? So if you end up with a greater than 1 number here, something went wrong in the process. So we are indeed less than 1. That's okay, but it's still a bit funny as a result. Once you have that, now equate your equation to the standard form and find the value of k that it gives exactly this damping ratio. And with that, the value of k now determines the percent overshoot of the system. And when you plot the time response of it, for a unit step input, we'll go to 1, and it will follow something like this. And this percent overshoot here, this maximum value cannot be higher than 1.08. The settling time we can also find now, and the settling time is simply replacing k back here, finding the roots, the real and the imaginary component, and this would simply be 4 over zeta omega n, which we actually have here. We have k, we have omega n, just replace, we have zeta, that's that, we have omega n from here, and this gives the settling time of the system.